So hi everyone, today we'll try to understand what are different methods to estimate test error for a classifier or some other model. So let's get started. So setting up the base, assume that you have a model A and you train it on some data set X. Now eventually the training error looks pretty low. So you wish to deploy it in production. What you would do first before deploying it into production? I think you would be checking its error with the validation data set that you have kept aside for pretty long. Like this is something that I have been doing for long, but now eventually there are a couple of questions that can be asked. Does this method, like using a validation data set and checking there has any loopholes? If yes, what? And are there any other methodology that we can use, like instead of just having a validation data set, to estimate over test error? I think let me answer the two questions. The first one being, like, the validation data set has some loopholes. A big yes. So for example, assume that you have just 100 samples in a training data set. Now dividing such a scanty data would create two major problems. One is that, as your data set is already very small, what you would wish to do is that you would wish your model to train on the whole data set rather than creating some samples out of it and create and training it on a subsample like 80 or 70 samples. Eventually model won't train that well. Second thing is that even if you divide this data set into two parts in validation and training, eventually the validation set would be very very small, like 10, 20, 25 samples. Would error estimated on these 20-25 samples make sense, or like is this significant, statistically significant? That is the question that I leave up to you. I feel no. So because what you would wish to do is to you should have a decent amount of data for validation as well, because like in case of 10-20 samples as a validation data set, even minor errors, like if you have big error in one of the samples, I think the model will just blow off, and eventually it won't be able to replicate the performance of the model correctly. Also, one more point to add, like assume that there are two models A and B, and eventually both of them has lump sum the same validation error. Which model should you pick up out of the two? So this is something around the complexity of the model which is not included in validation data set. According to the principle of parsimony, it states that if two models have the same error rate, the model with the lesser complexity should be included, should be chosen. But in validation dataset, as you have seen, it doesn't have any clue on the complexity of the models. So this is not included in validation dataset. So you saw how you can be in a tricky position if you're using validation dataset alone. So validation dataset misses out on some major factors like model size, latency, issues with model deployment, etc. So there was a competition held by Netflix that you must have heard of, where eventually the prize-winning model just wasn't deployed because of its humongous size. So again, all these points show that how validation dataset can be a failure at times, and eventually we should have different methods alongside for us for test error estimation and not just validation dataset. So let's understand what are different types of method. First of all, a resubstitution error estimate. So resubstitution error estimate is very simple and very naive. It states that if you don't have any validation data set, assume that your training error is the validation error. It's very naive, as I told you, and it has many loopholes, but still one of the basic methods when you don't have a validation data set. It's very hyper optimistic because eventually it is a training error is a very very poor estimate of test error, because on training your other model has already seen the data. Eventually it doesn't make much sense. But yes, if you don't have validation data set, a resubstitution error estimate can be your go-to method initially. Pessimist error estimate. So basically, it is able to cover up two major loopholes created by validation dataset. One is that if you have very scanty data, you don't wish to divide a model into a validation training dataset. Rather, you would wish to train your whole model, your whole dataset, whole model, your model with the whole dataset. Second thing is that it also includes the idea of model complexity in the final error estimate. So which was validation dataset was missing out. So let's understand what does this do. So the final test error estimate is given by et plus omega t upon nt. So let's understand what are these different terms. Et refers to error over training data set. Omega t is a penalty constant, is a penalty term, and upon n is the total number of samples. So error estimate, training error is something that we already know. Total samples we already know. Now what is omega? So omega is calculated depending upon the model using model complexity. For example, for decision trees, This term can be calculated using number of nodes in the tree into penalty constant. Now penalty constant can be any constant, 0.5, 0.7, 0.8, whatever you wish to keep it. Similarly, for a neural network, it can be total number of nodes in the entire network into penalty constant or total number of hidden layers, whatever you wish to do it. So eventually, omega is a flexible term which whose definition changes according to the model given. But yes, as you can see, then pessimist error estimate, what we are doing is eventually we are taking the training error plus the model complexity in terms of omega divided by n. So a few drawbacks to pessimist error is that as again nothing from the unknown samples has been seen, it can again go wavered as pessimist error as we don't have a separate validation data set. Determining complexity for few of the models can be very tricky. Like for example, KNN, K means what should be your penalty constant. Like in case of neural networks, you are using total number of nodes, total number of hidden layers. In case of decision trees, you were using total number of trees or total depth. But in case of Canon, what should be the K? So again, these are a few questions that can be that may create problems for you depending upon the model. Minimum description length principle. So this idea comes from information theory. Let's understand what is this principle about. Assume that we have two systems. One is X and other is Y. Model X is a model A which has the training data set as well as the target values also for the training data set. That means the ground truth. Now, for in case of system Y, it only has just the training samples but not the target values. So now Y can send all the information about the training values, the target values about the training data set to the system Y with a cost of n bytes of information, where n is the total number of records. So one byte for every information set passed. So it's just an assumption, like it's just an example that I'm trying to give. Or alternatively, what X can do is that it can train a model, assume it to be XYZ, and eventually send the model to system Y, so that when as it has already has a training data set, eventually system Y will generate the labels using the newly trained model XYZ. But what if the model that XYZ that has been trained by system A isn't 100% accurate? So in that case, system Y will get some sort of wrong labels as well. So you're getting my point, right? So what we're trying to do is that system X wish to send system Y the target values for the training data set. Uh, Eventually, sending them in a raw format would cause them n bytes. So what it is trying to do is to train a model XYZ and eventually send the model XYZ to Y, so that as it has the training data set available with it, it can predict labels for the training data set and eventually can have the labels for the training data set as well. But now as it is saying that XYZ can be erroneous as well, so Y might get some wrong labels as well. So the total cost of transmission from X to Y is estimated using cost of encoding the model plus cost of samples that are misclassified by the model less than n. So if cost of encoding model is equals to the complexity of the model. Now again, complexity of a model is uh, the definition for complexity will change for different from model to model. Again, we can use the idea given by pessimist error estimate, where we are taking certain parameter from the model, taking it as the core for the complexity, and eventually calculating penalty constant. Similarly, in case of cost for encoding a model can be taken in terms of complexity of the model. So like neural networks can be total number of layers or nodes. In case of decision tree, it can be the depth. Now, there are a few points that we should know. The model is 100% correct, then the cost of samples misclassified by the model equals to zero. Apart from that, whichever, like if you have multiple models to be tested out, to be that are competing against each other, whichever model gives us a lesser value for cost of encoding plus cost of samples misclassified should be considered as our final model. Estimating statistical bounds, so being the last one, again, as it is assumed that a validation or test error is mostly greater than the training error. So eventually what we can do is that we can add a constant to the training error and take it as a validation error for now. we won't be subtracting, because it is mostly assumed that validation error would be more than the training error, as it is on the unseen data. Now, for in case, now this can be done using, like as I've said in a very naive way, that we can add a constant, but this can be a very complex formula. Like for example, decision trees, this is the formula that is getting followed, which looks very complex. So we won't be deep diving into the formula, but yes, statistical bound states that key, eventually, as validation error would be usually more than training error, we add up a constant or like use some formula to add up on the training error and take the final value, the training error plus the penalty constant sort of a thing only, uh, and take it as our final estimate for the test error.